name's Bernhard. At the moment, I'm probably mostly the person who keeps you from the conference dinner. I'm not that. I'm a PhD student of John Pearson. And this presentation is about a paper we finished last year, which, as said, is about diagonalization-based approaches, which we've already seen for forward problem. But in accordance with the theme of this afternoon, it aims at optimization problems, optimal control problems. And this is based on things that already have been explored. So diagonalization-based approaches for optimal control problems is a known thing that works, which has been explored, for example, for the heat equation. And we just looked at a more complicated problem, a coupled problem, an instationary flow control problem, and solve how we can extend it and how it performs there, and which ways we have to come around the added difficulty associated with the coupled problems. Just to give you a brief overview, briefly gonna talk about the goal of this talk, just 2 slides. I will introduce the problem for which is the optimal control of instationary flow control problems. We look at 2 linear ones, Stokes and Usain flow control problems. Then we look at the first one, which is the easier one, the Stokes problem, see how we can devise a parallel in time preconditioner for that one. We move on to the Usain problem, which is then an extension of the Stokes one. And we're gonna conclude with a few numerical experiments showing the efficacy of the method, and I'm just going to conclude with some remarks about future work. So, like we've seen before, we are interested in PD constraint optimization problem. A very specific form, or maybe the simplest example, is the heat control problem. It's called heat control problem because we have the equation here, u dt minus the Laplacian y equals some control u plus some boundary conditions. What we're looking for is we want to match the state to some desired state while still analyzing the control that we put in there. The thing with these problems is upon discretization, they lead to large-scale problems. So one has to come up with efficient solvers for them. That is known for quite some time. And these problems are on top of everything also sparse. And how one proceeds about that is one tries to come up with an efficient preconditioner for it and then embeds in some Krylov solver. And as we all know, parallelization in space reaches its limit at some point, especially for large-scale problems like for fluid problems. So we seek parallelization in time. And one specific time method is diagonalization, is a diagonalization-based method. And that's what we are going to pursue. So it's going to be a diagonalization-based approach for optimal control problems, but specifically for the fluid flow problems. And we're just going to stick to linear ones for now. Non-linear ones are just part of future work. But we'll also see why we need linear flow control problems. So we want to devise a parallelizable diagonalization-based preconditioner fund. The problem itself has this form. So we have a minimization over V, a velocity space, U, a control source, P, the pressure. We want to solve this tracking problem. So we have some desired space, which can depend on an X and T. And we just want to match that and have some distributed control. And it is called instationary Usain flow control problem because the constraint is just the equation for the Usain flow. So we have here, well, time derivative, we have some diffusion, we have some convection, then pressure, and then this non-compressibility condition here. Plus some Dirichlet boundary conditions are assumed, and of course we need some initial conditions. And we arrive at the Stokes equation. If we simplify it, we're just setting the wind W to 0. What's nice about that is that we have then only a symmetric differential operator here. Because if W is not 0, that is asymmetric. And in order to solve the optimal control problems, we pursue a first optimized and discretized approach. What one arrives at is the first order optimality conditions, which are sufficient to solve because we have a convex optimization problem with linear constraints. And the first one is what we've already seen today, is the state equation, almost unchanged. Then we have an adjoint equation and the adjoint variable lambda. Technically, we'd also get a gradient equation. Here was just plugged back into the equation. because one can just reformulate u being 1 over beta L for the nodes. Yeah. And that's all what we want to really solve. And we try to come up with good methods, good linear solvers to solve these equations. So we then discretize them with finite element methods. We chose Taylor-Hood discretization. Taylor-Hood is a coupling of P2 and P1 elements, P2 for the velocity, P1 for the pressure field. We chose them because they're stable. As simple as that. And in time, we discretize with an implicit Euler method to avoid instabilities. And what we have then is this discrete system. So we want to solve a linear system with this matrix here. NT is the number of time discretization points, or is the step size that of the time discretization. M is the mass matrix. L is the discretization of the differential operator in space. So in the Stokes problem, it's just negative diffusion. In the case of the Ursine problem, it's negative diffusion plus some wind terms, some convection terms. And also B finally is, so B transpose is the gradient and B the divergence accordingly. And E is, it just arises from the time stepping and has this lower triangular structure, which, like in any case for diagonalization-based approaches, leverages this specific structure. It's almost circulant, but we're gonna get to that later. The only thing what we have to keep in mind is just that we have loads of sparse matrices and overall this nice Kronecker product structure which can leverage. So we look at the simpler case first, the Stokes problem. If we slightly rearrange the problem, it isn't that clear anymore that it's a cell point system, but it's just nicer to treat in a parallel time fashion. So what we have then here is in the first part here of the Kronecker product, only matrices are relating to the time discretization, time steps, and here in space. So here we have the time stepping matrix and some identities. That's all we have. And as a preconditioner, we propose or like it has been done before too, we use the circulant approximation of the time stepping matrix. So the only thing we have to introduce is a -1 up here. One has to be aware that even though one can use an epsilon there, minus epsilon for the diagonalization approaches for forward problems, that is not possible for optimization problems. That has been shown because they have to be, because C and C transpose have to be simultaneously diagonalizable by the Fourier transform. The only scenario that can happen is if you plug in epsilon being 1. So there's really nothing you can do about it, unfortunately. And oh yeah, so I mentioned before that in this specific case we have L being L transpose. So that's the discretization of the negative diffusion. And well, the advantage is that now we can diagonalize the operator because a precondition is only really effective. We can invert it or apply its inverse effectively. And that is a good approximation. So if we have some block form of the Fourier transform being applied to the left and the right, what we get in here is, well, the identities stay here and here and here, and the circular matrices result in diagonal matrices with the eigenvalues of the, sorry, with eigenvalues being the Fourier transforms of the first row of the time-stepping matrix. Also, just to mention, NV is the number of degrees of freedom for the velocity space and MP for the pressure space. And well, after all, this means that applying this, the inverse of the precondition is simplified to applying this thing in between because the Fourier transform in this block form can be applied quite easily. And it is simplified because it has a block diagonal structure. So it is a G upon permutation, so calligraphic G has block diagonal blocks Gj, which only relate to some spatial matrix. So what we have here is Dj, which are the diagonal entries of the Fourier transform of the circular approximation of the time-stepping matrix, and everything else just there's no new variables. So if you want to apply the inverse of calligraphic G, one can simplify that to applying the inverse of each Gj. is then nice because that can be done all in parallel, because it's off block diagonal structure. I think it's quite clear it works, but if we just once more, so we have some residual, we have some time points, and each residual has then a few entries in space. One applies the f of t, gets an r hat. Then one can apply all the GJs in parallel. The inverses of them arrives at some s hats, and then by applying the inverse f of t, one arrives at the solution. Well, the solution. And one can show nice properties about this this preconditioner. So the eigenvalues of the preconditioned matrix PC inverse to apply to A, which are 1, is quite large. So the only number of degrees of freedom that we lose that are not 1 are of order 2 times NV, so independent of the time discretization. And that is nice because a GMRes usually can deal with these things quite nicely. So, well, for GMRes, it is nice to have eigenvalues 1, and even if it's just a few which are not nicely clustered, it manages to capture those in a few iterations later on. So that gives us a good feeling about that GMRes might work quite nicely. And that is actually also the case if one just plugs it in and uses actually the inverse of that one, one can see that you get convergence quite quickly within 3 or 4 iterations. But the problem is solving all the GJs is still not a very easy task. It is still a quite complicated matrix. You have a saddle point system of a significant size. So one has to come up with good solvers. Fortunately, there's lots of work for these kind of matrices. So for example, Kendall, Simoncini, and Zulena have already looked into the periodic in time solution of periodic in time optimal control problems for the Stokes problem. And what they leverage is a block diagonal preconditioner with some matrices which can be assembled by all the mass matrices and differential operators. And then for these terms here, the Schur complements, use a commutator argument for the divergence and gradient, which allows one to replace this nasty matrix here, which is nasty because these are not square matrices, with this concatenation of square matrices. So inverting that one is much, much easier, especially you have here a mass matrix in the pressure space, which is easy to invert with the Chebyshev semi-iteration, for example. And also we have some stiffness matrix, which can then be solved with some algebraic multigrid or whatever one prefers. And that preconditioner will be denoted as PJ hat. So there is ways to actually solve the subproblems efficiently. However, if we just the original result is only for when the inverses are applied exactly on all the subblocks. That's something that we can achieve very quickly. So we had a first idea, which was the first idea for the precondition. Instead of applying the inverse of the GJs, we already have a good approximation, which is given by P hat J. So why not just replace it? All the GJs with PJ hats. That is denoted by PC hat. And what one can actually show then is if the preconditioner for the subproblems fulfills this property here, that we have 2 bounds, A hat and B hat, both being positive, and it's contained in that interval. That property carries over to the circulant approximation-based preconditioner. So the number of eigenvalues which are contained in that interval is also quite large, and you only lose about 4 NV of those. This also suggests that it might work quite nicely. We verified these results, so we looked at some small matrices and computed the eigenvalues. So first off, we have the circular approximation with the exact GJ. There you can see most of the eigenvalues are 1, just a few. The low rank per dB, just indebted to the low rank approximation, are not 1. If we then look at some approximation of the GJs, we get these approximations. So these lines here are these A hat and B hat. And if we apply that to the original system with the circular approximation, we see that these are still contained within these bounds, but just a few are kicked out. So those are the 4 NV or less, or max 4 NV, which are kicked out. So that all aligns with what we found. But unfortunately, that precondition doesn't perform very well. We saw that if we embed it in GMRes, we still get about 150 iterations till convergence. And we tried to apply it, and then communication just prevailed, which led us to another idea, which is instead of using PJ to replace it, we just solve the subsystem to a certain accuracy, which then gives us a nonlinear preconditioner. So the in the original preconditioner, we would have this whole a routine where we first apply the Fourier transform, and for each time step in parallel, we do some block row manipulations. And before that, we would just apply PJ hat, and then just reverse all the transformations. But now we just plug in a GMRes here with this submatrix, which relates to GJ, and this precondition, and solve up to as the tolerance epsilon just predefined in the beginning. And that turned out to work much better. The only caveat here is you have to apply it within an FGMRes, which means that if you have the iteration of the Krylov solver, you have to keep in mind that you have to save all the vectors. So it might be good if you have only a very small number of iterations, which luckily turned out to be the case, because otherwise you might have a problem, because if each vector, I don't know, has a gigabyte, that becomes a problem. So that was the working method for the Stokes problem, and that idea can be adapted to the seam problem. Oh, I forgot. Just to give an overview, if you want to apply that solver now for your problem, yeah, in the outermost level, you have a flexible GMRes. Then you have a few FFTs, transformations in here. And then you apply a GMRes, where it's solved into this tolerance. And then for all the finite element matrices, you use standard methods like a fixed number of iterations of multigrid. For approximating the Schur complement, or based on the commutator argument, you use some Chebyshev same iterations for mass matrices, multigrid for KP. Exactly what I mentioned before. It gets much easier at that level. Yeah. Simple. And and if you move to the seam problem, it is quite similar. So the whole diagonalization process works the same way, maybe not the same way, but in a similar way. Because L is not symmetric anymore, you have to separate the parts, but that's all you have to do, and the whole machinery just works the same way. What you'll end up with is a matrix GJ, acting the same way as it did before, but here we don't have an L and an L here, but we have an L transpose, again, because of the asymmetry. And what we did here is we have a cell point system structure, so a 1-1 block up here, then the 1-2, 2-1 block, and here we have 0. So what we thought might be nice to apply is use a triangular preconditioner for that. So we set that block to 0. We approximate that block with an Usava iteration, which we can apply because we have good estimates, and we have a good preconditioner for this system there, based on a matching argument. And then for the Schur complement, we plug in a commutator argument, similarly to the one before.
Is the vecting velocity time independent?
It is time independent, yeah.
Otherwise, you have to do some averaging or something like that for the.
Yeah, then you would have to do that. Yeah, it's true. So yeah, it doesn't work if you have too much nonlinearity. If it's a linearization, and soon it is an iteration of a Navier-Stokes equation. That's right. Yeah. Yeah. So now we have the two solvers. That one is quite similar. So we have a flexible GMRes again, GMRes for the GJ blocks. For the 1-1 block of the GJ, we use an Usava method, which is then based again on some Chebyshev semi-iteration for inverting the mass matrices. A multigrid method for some other matrices, finite element matrices. And here we just have the same story again for the Schur complement. And yeah, now we're in a place to look at some numerical experiments. So our example problem is we have some instationary forcing, and some also inflationary desired state. Maybe stationary desired state. Final time is fixed to 1, and we vary a few parameters. The first one we're going to vary is the spatial discretization. Then also regularization parameter beta, because that always has a big influence on the performance of optimization solvers. And also the number of time steps, obviously, because that's what we're interested in. We just want to push it to its limits. The inner tolerance of the GMRS is set to 10 to the minus 2, but some tests also have shown that 5 times 10 to the minus 2 might be, so 0.05 might be already enough. So it's not really, we don't have to solve it to a very high accuracy in there, which is nice. So the first one is the first table is for the numerical experience with the Stokes problem. So here we use, well, it's a 2D mesh. Here we have a maximum cell size of 1/64. The spatial problem has approximately 60 to 70,000 degrees of freedom, somewhere in that order. And here we have several time discretizations, and on this dimension we have different regularization parameters. And what's shown here is the number of degrees of freedom, obviously growing with the number of time steps. And for each setting of the regularization parameter, we have the number of FGMRS iterations, so that's the outer loop, and then the average number of inner GMRS iterations. And here we have the CPU time, and it's all in serial. We're going to get to the parallelization part later. And where it says star, and that's just when it took a bit too long for me to run it in serial, and yeah, just didn't get enough resources. So I ran these results are based on parallel experiments. And what we can see here is that the number of out iterations remains quite robust with respect to all the parameters, and similar things hold for the number of inner GMRS iterations, which is quite nice. And that's actually also what we are looking for here. So the CPU times should grow linearly in time for it even to be a good candidate for a preconditioner. I mean, with respect to the number of time steps. And what we can, yeah, and here we can see by doubling the number of degrees of freedom, we get circa double the number, double the runtime. And similar results hold for the scene problem. So it's the same. We have a few more FGMRS iterations. The number of inner iterations is quite good. It's not too many of those. Yeah. And now to the maybe more interesting part of the numerical experience, we looked at strong scaling. So we just fixed the problem size. Here we look at about 70 million degrees of freedom. We for the fine problem, which is denoted by HF, and for HC, it's about it's double the H, so double the cell size. It's a bit of a smaller problem. And we can see if we just add the number of cores that we get quite nice scaling. It's not ideal, but that's not what we would expect. But at this point here, we have 2 time steps at each core. So we almost get down to the very low part. We get good scaling behavior, well, consistent scaling behavior. That is for the Stokes problem. With the scene problem, we would expect a better scaling behavior because the subproblems become slightly harder. So we would expect to see more advantage by distributing that workload. And that's also what we observed. Because here, before we had about factors NP to the NP being the number of processes to the minus 0.7. Here we have, in the case of yeah, in both cases, we have about 0.75. Oh, no, we don't. 0.83 for the other one. That's still good scaling results. And maybe as a last scaling result, I mentioned before by replacing instead of solving having an inner solver and solving the subproblem to a certain tolerance, we had the initial idea to just replace the preconditioner, and I'm just gonna put in the results there. So the reason why we didn't pursue that is because we saw that we already reached. We didn't get any advantage by adding any cores because we had so much communication in the end. So it was necessary to solve the subproblems. And also in the theory, it suggests that the only problem is maybe only that the interval is just a bit too big, because in the case if the exact inverse, the preconditioner worked quite nicely. So if it's 1, so what we basically did here is we squeezed A hat and B hat just a bit closer together to 1, where it actually worked better. Okay. So that leads me to the conclusions. So what we achieved is we developed an efficient parallel time preconditioner for unsteady Stokes-Levine flow control problems, all of them linear and time independent. Yeah, as I said, it's parallelizable in time, and we've seen that it has good strong scaling behaviors, and yeah, it's robust with respect to the model parameters. All the future work's been, I don't know, this slide's been standing there for quite some time, since a year actually, on this set of slides. We're working on how we can extend this to autonomous nonlinear problems. I've been working on that, but I realized we had to work on another project for that first to actually justify to use that, but hopefully at some point we'll have some results. So we'll see. But yeah. And because it's maybe not appropriate to say thank you for the very last talk before the conference dinner, I'd really like to say cheers, but we're in Scotland. So one has to say, if somebody's done a Scotch tour already, that's Slàinte is what we say here. So maybe if you find yourself with a good pint, maybe with a smaller case tea, later you can impress the one or the other Scottish person. So with that, Slàinte.